Good morning. Welcome to the webinar, everyone. This will be covering the STM32L4 series of microcontroller. This is based on the 32-bit ARM Cortex M4 core. The STM32L4 series is part of the STMicroelectronics 10-year product longevity commitment program for the STM8 and the STM32 microcontrollers. So there'll be no problem with designs forwards with the designs supported for 10 years from design start. I'll just move through some of the main advantages of the STM32L4 ultra-low-power microcontroller series. These are ultra-low-power leaders and performance boosters. ST has built a new architecture to reach best-in-class low-power figures thanks to its high flexibility. Moreover, the performance of the STM32L4 series adds a new dimension to the ultra-low-power world. It delivers 100 DMIPS based on its ARM Cortex M4 core with FPU and ART Accelerator at 80 MHz. We'll cover the ART Accelerator, the adaptive real-time accelerator later. Innovation. To address a large market range, the STM32L4's architecture implements several innovations on its architecture and it embeds several smart peripherals. Integration and safety. The STM32L4 integrates up to 1 MB of flash and 320 kilobytes of SRAM. There are also several safety and security features and numerous peripherals, advanced and low-power analog circuits in packages as small as 3.13 and 3.14 millimeters. There is a wide ecosystem for the STM32L series and F series. All of them are pin-to-pin compatible, and the software tools span the whole range. Within the range, they range from 32 MHz up to 200 MHz, so depending on your application, you can migrate from one series to the other with very little difficulty. The new STM32L4 architecture implements several and many innovations to reduce power consumption and increase flexibility. A new low power mode has been added, shutdown mode, with consumption as low as 8 nanoamps for I/O wake up. The real-time clock is available in all power modes. A dedicated pin, VBAT, can be connected to the backup battery. There is an automatic switch between the main power supply and this VBAT pin, and as soon as the main power goes low, the automatic switch activates, which maintains the power for the RTC and backup registers. There are several oscillator modes. No need to have a dedicated crystal oscillator for USB by using the internal high-speed 48 MHz oscillator. There's also a MSI internal oscillator, which can be programmed from 100 kHz up to 448 MHz with a very high accuracy, plus or minus 0.25%. This is enough for the USB peripheral with a low-speed external crystal to calibrate it. All I/O levels can be retained in low power mode, as well as during wake-up phases, which optimizes the system power consumption. The flexibility of wake-up sources has been increased, allowing more peripherals and events to wake up the MCU from any peripheral. We also have a standby mode down to 200 nanoamps with partial RAM retention. The RAM retained is 16 kilobytes. Optimized active mode. Thanks to an external switch mode power supply, the supply to the core can run down to 36 microamps per megahertz, which is very good. Some I/O pins have a dedicated supply, V-domain, voltage domain. This is in order to avoid having to use external level shifters, so part of the STM32 can run at 1.8, 2.8 volts, etc., and interface to a GSM modem directly, and other sub-circuits running at different voltage levels. So there's a couple of really nice features there: crystalless USB, the flexible MSI, the RTC backup, and the secondary voltage domain, and the RAM retention at 200 nanoamps. Moving on to slide 4, these are the power consumption in different modes. So the STM32L4 offers best-in-class power consumption with flexibility. The user can select the best operating modes depending on the wake-up time, state of retention, and number of sources required. VBAT runs down to 2 nanoamps without the RTC and 200 nanoamps with the RTC. Shutdown mode at 8 nanoamps without RTC and 200 nanoamps with the RTC. With this mode, you can wake up from 5 IOs, the reset pin, or the RTC. Standby mode has the possibility to keep 16 KB of RAM in retention with more wake-up sources. The wake-up time is 14 microseconds. There are 2 stop modes, stop 1 and stop 2. In both modes you contain all the memory and all peripherals, and it takes less than 5 microseconds to fetch the next instruction. The difference between the two modes is that you can wake up from one UART and one I2C in stop 2, which is why it's slightly lower power, while in stop 1 you can wake up from all the I2C and all the UARTs. There is also a sleep mode used to wake up from any event or any interrupt. This is at 10 microamps per megahertz. The STM32 allows a very low power consumption active mode down to 36 microamps per megahertz in run mode with the external switch mode power supply, and at 80 megahertz it's 38 microamps per megahertz. So it's got a lot of sleep, standby and stop modes, all very good power consumption in all of those. Slide number 5. So the STM32L4 shatters performance limits in the ultra-low-power world. It delivers 100 DMIPS based on its ARM Cortex M4 core with FPU and STR Accelerator at 80 MHz. Once woken up from stop mode, the internal clock is available in less than 5 microseconds when running at 48 MHz and 20 microseconds when running at 80 MHz. The STM32L4 MCU scores 217 in the standardized EEMBC ultra-low-power benchmark test that compare the efficiency of ultra-low-power microcontrollers. And those tests are available for you to look at. Now, slide 6 represents the ART Accelerator, the Adaptive Real-Time Accelerator. Thanks to this, there was linear performance with frequency and there was no impact on flash states. The STM32L4 reaches 100 DMIPS or 273 core mark with the M4 core with floating point and the DSP instructions. It also embeds 2 DMA controllers allowing up to 14 channels and several high-speed peripherals including 40 megabits per second the SPI and 10 megabits per second UART. The STM32 microcontroller implements many innovative and smart peripherals. To illustrate this, we're going to look at a few examples. The first of these is metering. It is a very good fit thanks to the 8x40 segment LTD controller, the 3 tamper detect pins, communication interfaces for connecting to SPI, UARTs, SDIO, and also for interfacing to wireless devices. A lot of IOs, a parallel interface for connecting to external memory, the Flexible Static Memory Controller, FSMC as they call it. Hardware crypto, so true random number generator and the AES engine, both used for security, and then the VBAT with the RTC domain, and the possibility to connect an external sigma delta modulator with the DF-SDM interface. We're going to move on to a second application now, which is fitness trackers. So this is a very good fit because it also has a TFT display which can be interfaced with the FSMC or the SPI, USB host or device, that's USB 2, serial audio interface, and a lot of analog IPs such as the op amps, the DACs, the ADCs, which we'll cover in more detail later. It also provides a secured element connection via the single wire protocol, the SWP, numerous serial connections, a batch acquisition mode with the possibility to retrieve data from the sensors while the MCU is in low power mode to reduce the power consumption further. And again, the DF-SDM also supports the direct connection of digital microphones, the filtering and data conversion of which are done in hardware to further improve the system power efficiency. So that's the fitness tracker. We'll now move on to the industrial sensors. So again, a very nice product for industrial sensors. Especially where power constraints are an issue. Its 8x40 segment LCD controller is much loved in the industrial sector. Numerous serial interfaces and IOs, as well as the flexible static memory controller for connecting to external memories. Ambient operating temperature range up to 125 degrees C. All make the STM32L4 an excellent choice for industrial sensors. In addition, it embeds the encryption hardware accelerator, true random number generator and the AES, SHA encryption, a CAN bus 2 interface, and motor control support with the advanced timers on 3 analog to digital converters. And this all also runs on the FOC field-oriented control motor control library that ST provide. So those are 3 applications. Just going to cover some digital smart peripherals that are internal to the device. So in stop mode, there's a low power UART. So this can wake up the system if a program byte is received or on the start bit is detected, or if a start bit is detected. The I2C interface can wake up the system when a specific I2C address is detected, which is a very nice feature. And there's several low power timers can count time and generate events and signals in stop mode. Sorry, excuse me. There's also a quad SPI interface for data and code execution in place, so you don't need to load that code into the internal memory to run from that code. The DF-STM interface, as already discussed, can be connected to external sigma delta modulators, for example the STM32. It also supports digital MEMS microphones, such as the MP34 series from ST, with hardware conversion and filtering from PDM to PCM mode done in hardware. The peripheral clock is independent from the system clock, and there's also the single wire protocol for smart cards. So that covers a lot of the new digital smart peripherals that are with this MCU. We also have some analog peripherals that ST likes to call smart. There are 3 12-bit ADCs and a single 16-bit ADC. These run up to 5 megasamples per second. In 12-bit mode, they support low power modes down to 20 microamps with adaptive power consumption. And in 16-bit mode, it uses hardware oversampling to get to that level of bit depth. Both single-ended and differential inputs are available. There are also 2 op-amps with a programmable gain array, 2 12-bit DACs at 1 megasample per second, and 2 comparators complement the above features. There's also an internal voltage reference which can be programmed to 2.048 volts or 2.5 volts, and this can also be used externally. So slide 12, which is labeled 14 unfortunately, the STM32L4 has a very wide variety of memory sizes, up to 1 megabyte of dual bank flash and 320K of RAM, and as low as 128K of flash and 64K of RAM, I believe. The STM32 microcontroller embeds many peripherals, including a total of 17 timers, up to 136 IOs, and a touch sensing controller. And again, they're available in sizes down to 3.13 by 3.14 millimeters and your standard QFN L2FP packages. For the safety and security, there's brownout, detect, clock security system, SRAM priority checks, etc., etc. An error correction code is available which warns the system if an error occurs and tries to correct it. There's a dual watchdog. On the security side of the system, there's also the 256-bit AES and 256-bit SHA encryption engines, the JTAG fuse, the anti-tamper detection pin, a unique ID, and software IP protection features such as and also the true random number generator. So there's a lot of features for making sure that your design is safe and secure. So I just want to move on to show you how the STM32L4 series fits within the STM32 ecosystem. What is great about the STM32 portfolio is that it offers an extraordinary variety of compatible microcontrollers based on the ARM Cortex M cores. There's M0 offerings, M0 Plus, M3, M4 and M7 cores, giving developers flexibility to find the perfect match for their applications. The STM32L4 is a great investment and benefits from pin-to-pin compatibility across the STM32 family. So whether you're running from 32 MHz up to 200 MHz or 400 MHz with the H7 part, there will be a part to fit no matter where you start your design, no matter which product you start your design on. So I'm just going to delve a little bit deeper into the L0, L1 and L4 families. So the STM32L series MCU is the largest portfolio of ultra-low-power MCUs that exist today. This series is at the heart of many battery-operated or energy-sensitive applications. The L1, the STM32L1, has a broad range of products and is the foundation of the STM32 ultra-low-power series. The L0 is the cost-smart ultra-low-power champion microcontroller series and is based on the Cortex M0 Plus core. So there's not much in the way of DSP, but it is a very low-power core, and it is very cheap compared to the L1 and the L4. The STM32L4 completes the ultra-low-power microcontroller series, providing more best-in-class power consumption figures, higher performance, more advanced peripherals, and more memory. So this slide just shows you where the DMIP scores and the Cormark scores are between those three ranges, and where the L4 sits, covering the bulk of the designs between the L0 and the L4. So we'll move on to slide number 17. There are a variety of parts across the STM32L4 series. The access line, the entry-level part, is the STM32L431. This includes the standard peripheral set with up to 256 KB of flash and 64K of RAM. The STM32L44 series adds peripherals such as crystal-less USB interface, the 8x40 segment LCD driver, and the AES engine. The 471 series increases the flash and RAM from flash and RAM to 1 MB and 128K respectively. Further additions to the series, such as the L475 and the L476, add the USB 2 on-the-go peripheral and the 8x40 segment LCD driver. The newly announced STM32L496 and 4A6 increase the RAM further to 320 KB. The flash is still 1 MB, but the L4A6 adds the AES and SHA encryption hardware as well. Further showing the portfolio here on slide 18, the STM32L4 series is available in a range of package sizes and memory footprints as shown by this slide. The AES encryption hardware Accelerator is optional across the range, so we can see we've got 32-pin QFN packages up to 169-pin BGA packages, with 6400-pin packages in the middle, with 128K flash, 64K RAM, through to 1 mega flash and 320K RAM. So showing discussing the ecosystem that is available with the STM32L4 in a bit more detail. On the left we will see we have Nucleo boards which provide all the pins of microcontroller for you to play with. From the discovery kits in the middle generally highlight specific features and are targeted at specific applications such as display, interfacing to MEMS devices, wireless connectivity, or SDIO interfaces. The last option is full evaluation boards that demonstrate how to get the most out of the full range of peripherals and features for an STM32 microcontroller. For all boards, there are expansion boards to add analog, MEMS, motor control, and wireless connectivity with a complete set of companion boards and software tools. On the right-hand side of this slide, we've got some software tools. The STM32 Cube MX tool is a graphical user tool which can intuitively select and configure an STM32 microcontroller that matches the user's required set of peripherals, as well as program the required embedded software. Based on user choices, the tool can also generate initialization C code and estimate power consumption of the STM32 MCU. If you haven't seen this tool, I would thoroughly recommend going onto YouTube and ST have a couple of presentations on it, and it is a brilliant GUI-based tool for getting peripherals, getting your hardware pins worked out and getting your peripherals configured for the right baud rates, the right clock phase, polarity on SPI, etc. All the things that we need to look at datasheets for typically now, but with this tool you generally don't. Move on to slide 20. This discusses the Cube software offering in a bit more detail. The STM32 Cube MX relies on the STM32 Cube embedded software bricks. They're zip files that are available online, but the Cube tool will download those and put them onto your hard drive in a well-organized manner. These are used to generate the peripheral initialization code. The first firmware layer of these embedded software bricks is made up of the low-level drivers, for example, the hardware abstraction layer, HAL, and the low-layer LL APIs. The HAL implements a high portability between STM32 series, while the low-level APIs bring a performance aspect to the STM32 Cube L4, offering reduced code size and improved performance. So just to note there that the HAL libraries are generally cross-platform compatible. So if you write some code for the L0 and want to port it to the L4, you can. The HAL abstracts the STM32 series from one another thanks to a highly portable set of APIs, thus ensuring an easy migration path from one series to another. The low-level APIs are a lot closer to the machine and constitute a lightweight, high-performance, expert-oriented firmware stack for maximum dynamic reactivity and flexibility. Last but not least, these low-level drivers are distributed under the BSD license, one of the most permissive and business-friendly open source licenses. For more convenience, the Cube L4 embedded firmware also comes with a set of middleware bricks. They are portable on any STM32 series that support the required functionality. So these middleware bricks also come for free, and most of them are based on either open source, de facto standards, or SD deliverables with permissive and business-friendly license terms. So these are things like the lightweight IP stack, the FastFS libraries, a BLE stack for their BLE system, etc., etc. In addition, numerous examples are provided to help the customer understand how to use the low-level APIs and the middlewares with the microcontroller. ST provides high-quality, low-level drivers which have been thoroughly qualified using both standard and ST-specific validation tools and processes. So we're starting to wrap up. Summary of what we've talked about today. The ultra-low-power, the STM32L4 is the ultra-low-power leader and performance booster with a wide range of cores, peripherals, RAM, and flash sizes. There are many innovative peripherals on board the device. There's an easy integration of peripherals and AES SHA hardware, true random number generator, and tamper pins, and there's a large ecosystem to fit many applications. It is portable across devices from 32 pins up to 200 pins. Okay, thank you very much.